Hello everyone. Now we'll start the chapter number 9 of quantitative techniques is the regression diagnostics. So this is the final part of your linear regression section. Okay. So first we started with the linear regression with one variable, then linear regression with multiple variables. So after your regression model is produced, we need to see if there is any problem with that model. So what can be the problem and how to identify those problems? This is what we are going to discuss in the regression diagnostics. So primarily there are three problems. The first problem is related to the heteroskedasticity, specifically conditional heteroskedasticity. Second is the multicollinearity, and then we will see the bias variance trade-off. Okay, so we will discuss all these three things in the detail. This chapter is primarily a very theoretical chapter because you cannot see the practical application of each and everything, because it is not the part of your GAPS learning outcome, and also this is not testable for your exam. Because it requires tools and some calculations, detailed calculations, to check if there is any problem with your model, right? So my recommendation is make sure you are good with the one linear and multiple linear regression analysis, the basics of model, because ultimately we are going to see what are the problems with that model. Before you begin, just take a look at the assumptions of linear regression model for both multiple linear regression and the one variable regression. Okay, and after that part you should start with the regression diagnostics. You can pause the video, read those assumptions, because primarily we are seeing that if the assumptions are fulfilled or not, right? So make sure you read the assumptions and then continue this chapter, right? So we will start the discussion. Here the first thing we are going to study about the heteroskedasticity. To understand the heteroskedasticity, first you need to understand the homoskedasticity. Homoskedasticity means variance of residuals. Okay, we are talking about the variance here, is constant across all the observations. So your independent variable, if you plot the variance against the independent variable, you should be able to see that the variance is constant. I will give you the example. What is the constant and what is not the constant? Okay, now just see this diagram. Okay, we are plotting your residual against the independent variables. Okay, there are multiple ways to plot this diagram, but here we are plotting like independent variable against the residuals. You can also get with the fitted values. Now in this particular case, you can see I'll just delete it. I'll just draw it for you again. So this is your residuals with respect to independent values. Okay, independent variables. Now if you plot residuals against the independent variables, if you are able to see that the variance is constant, how to check the variance is constant? See here, this is equal to this, and approximately you can see that the spread of your residuals is constant. It can be increasing, it can be decreasing. Okay, so if you get the graph like this, which is a decreasing graph like this, then don't worry, this is still a constant variance, constant across the independent variables or the observations, right? So as long as your variables, as long as your variance of residuals is constant, we call it as a homoskedastic. Homoskedastic means skedasticity relates to the variance of residuals, and then homo means the constant variance. Okay, so this is constant variance, that's why we will call it as a homoskedastic, right? So homoskedasticity is requirement of your regression model. So this should be the case. It can be like this. You can also get the variance like this, okay, and still this is the constant. The next is the heteroskedasticity. Now heteroskedasticity comes in two variations for our purpose. The first is the conditional and second is the unconditional. So first we will see the unconditional and then we will see the conditional. Again we will plot this same graph. This is your residuals, okay, and in unconditional your graph might look like this, okay. Now see what is happening here. So here your variance is very low. See, the spread is very small. Suddenly at this particular point variance starts to increase. So you have high variance. This point is the highest variance and then again it drops. Again it increases. Again it drops. Again it increases. Now this is heteroskedastic, meaning the variance is not constant. Variance is not constant but not conditional, okay. What is not conditional? Conditional means there is no relationship of change in the variance, that is a heteroskedasticity. Changing variance is not depending on your observation. So you can see that as you go along the observations, as the observations are the value of the observation is increasing, there is no fixed pattern in it, okay. So it is sometimes increasing, decreasing, increasing and decreasing, and there is no condition to attach to the your observation. So this is the unconditional heteroskedasticity. Now what is the conditional heteroskedasticity? You must have guessed. So when your variance, that is the heteroskedasticity, changes with the observation level. So as your observation value increases, your heteroskedasticity is increasing. That is the variance of your residuals is increasing. Just see here. You can see when you have low observation value, the variance is low. When you have high observation value, you have high variance, and same is applicable for all. It is systematically increasing, okay. So there is an increase and it is dependent on the your observation value, that is x here. So this is, we call it as a conditional heteroskedasticity. The conditional heteroskedasticity means that it depends on your independent variable, okay. So let's see the text now. Okay, so the first part was relating to the homoskedasticity. Now next is the heteroskedasticity. The first is the unconditional heteroskedasticity. The variance is not constant. That is, it is as we saw in the diagram, that it is not constant, but it is not related to the level of independent variable. Okay, so observation is not linked with the level of observation is not affecting your residuals variance. It is changing, it is heteroskedastic, but it's on own way. Then there is a conditional heteroskedasticity, which is the problem for our model. So conditional heteroskedasticity is the variances are not constant, or variance is not constant, but is dependent on the level of independent variables. Here we have one diagram. Here also you can see, this is a software generated diagram. Okay, you can see here your variance is increasing. So here you have small variance, here you have larger variance, the spread is increasing. So here you have residuals plotted against your x observations, right? So this is the problem for us. Now what type of problem we have? So first of all, you need to understand, like, we saw some assumptions. So assumptions relating to the residuals, assumptions relating to the your independent variables and so on. So what happens is, this is the part which relates to the residuals, meaning there is no as such problem with your model. Your model is good, But because your residuals are affected, you can recall your hypothesis testing chapter. We use standard error in hypothesis testing. So residuals are your standard error, right? And you are going to use these residuals for the t-stat calculation. So if you use this type of residual in your t-stat calculation, your t-stat will be problematic, and then hence your hypothesis testing is affected. Your model is good, no problem with the model, but your hypothesis testing is affected. This is the only problem with the heteroskedasticity. Why so? Because you remember, to get the benefit of standard error in your hypothesis testing must be distributed normally, right? So if the variance is constant, we can say yes. So here you can see the effects of heteroskedasticity on the regression model. The first is the standard error are unreliable estimates. So you cannot depend on standard error. Okay, so only problem is this. And hence the hypothesis testing is affected. So your only problem should be your hypothesis testing. And you should not rework your model. You have to simply recalculate your residuals using some certain methodology. And here the next part is the coefficient estimates are unaffected. Coefficient estimates are your beta 0, beta 1 and so on. Okay. So these estimates are fine. We can go ahead with the estimate. These are consistent and unbiased. So we don't have any problem with our model. You have to always remember this, that heteroskedasticity itself is not the problem for your regression model. It creates a problem in hypothesis testing because you cannot use the standard errors which are conditional, which are changing according to your independent variables level. So for this purpose, you have to correct it. You have to just correct or recalculate the standard errors using certain methodology, as I have already told you. So here see how to detect the heteroskedasticity. The first is the using scatter plot. So scatter plot we already saw how to generate the scatter plot, and again if you have the software you can easily generate the scatter plot. The second is the chi-square test. This particular concept is discussed in your book, but it is very half-cooked, so not a very detailed explanation and just a rough idea of what are the steps, and these steps are very difficult to remember. So I am giving you steps in a very theoretical manner or the intuitive manner. Okay, so you have to just see or imagine like what's going to happen here, or simply remember this particular part. And I don't think like you will get any question on calculation of the chi-square test because it is a lengthy process. Chi-square test for the detection of the heteroskedasticity and so on. Okay, so let's first see what are the steps. So this is step number 1. In step number 1, regress the squared estimate of residual with the original explanatory variables. So now you will do the regression of estimated residuals with your independent variables, explanatory variables. One thing, this is step number 1. Then conduct the hypothesis testing using the chi-squared statistics by calculating a chi-squared statistics using the coefficient of determination. So you will get the R square. Okay, you have to use the R square for the chi-squared statistics. There is a formula given there, and then you have to compare it with the critical value. Okay, and if the null is rejected, this is the important line you are supposed to remember. Ultimately, if you read the book, you will get this much idea only, but here I am giving you the lines which you are supposed to remember for the exam purpose. This particular part cannot be discussed in this manner. We should discuss, like if you want to get the proper idea, you have to see it practically happening, and that practically happening is not testable for your exam. That's why I am giving you the simple statements. Like you have to remember, the first you have to estimate. Just try to remember it with me. First, you have to regress your residuals from your original model with the original explanatory variables. This is the first step. Second step is you will conduct the hypothesis testing using the chi-square test, where you will calculate the chi-square test statistics, okay, using the coefficient of determination. Then there is a formula for it, like how you are supposed to do it. And third part is compare chi-critical value with your chi-square statistics, and if the null is rejected, means no conditional heteroskedasticity. This is the important point you are supposed to remember. If the null is rejected, means no conditional heteroskedasticity. What are the chances you will see question on this? Very low. Okay. Now next is the correcting heteroskedasticity. How to correct it? So first, you identified it. using the scatter plot or using your chi-square test. And now your concern is like correcting that problem, because this is your model and then you do the hypothesis testing. So our problem is related to the hypothesis testing. So we will work on this part only and not this part. So this is unaffected, right? So for this particular part, we will recalculate our residuals using this specific methodology, which is known as the white standard error. Okay. So as this particular conditional heteroskedasticity concerns the standard error in hypothesis testing, we use the standard white standard error, also known as, this is also known as the robust standard error, in the hypothesis testing instead of standard errors. We using software, you can just write down the 2 lines of code and get the white standard error and use it in your hypothesis testing. Not a very big deal. Okay. So what is the only difference here? For the calculation of your t-stat, your t-stat goes like your identified variable, that is your estimate, divided by standard error. Now this standard error will be replaced by your white standard error. So we call it as a white standard error. That's it. Finish. And everything is the same. Only difference is recalculation of this part for your t-stat part. Right? This is a very easy thing. White standard error is also known as a robust standard error. Please remember this particular statement, because if GAP asks you about the robust standard error, you should be able to correlate with that this is a white standard error. Okay, and what is a past trend? What type of questions you get in the exam? So questions are mainly relating to this, the combination of heteroskedasticity and homoskedasticity, and GAF will tell you like, see, the multicollinearity, or say heteroskedasticity is if the heteroskedasticity is present, then model is unreliable. So there will be 4 statements like this, and you have to identify which statement is correct, which statement is incorrect, and like that. And statement might also consist of like, to correct the heteroskedasticity you have to do this and that, and like that. Confusion generally occurs with the heteroskedasticity and the multicollinearity and the bias variance trade-off. Okay, so this is a general area where the confusion happens. So you have to separate it. So that's why I'm giving you the storyline, like what is heteroskedasticity, why it happens and why it is problem. Then we will see what is multicollinearity, why it happens and why it is problem, and then we will see what is a bias variance trade-off. So you have to understand these 3 concepts in a separation. Else you are more likely to make a mistake in exam. Like, see, multicollinearity causes problem with your model. Heteroskedasticity does not cause this problem with your model. So you have to separately remember these things, right? So let's see. This is about the heteroskedasticity. Then comes the important part, equally important like the heteroskedasticity, is the multicollinearity. Now what is the multicollinearity? So let's recall our regression equation. Your regression equation goes like this: b0 plus b1x1 plus b2x2 plus say b3x3 and your standard error, right? Now in this model, one of our assumption is all your independent variables are independent and identically distributed. Independent meaning they are not correlated, right? So if there is a correlation, we call it as a multicollinearity present in the model. Okay, so if these variables are correlated, like x1 is correlated with the x2, or all 3 are correlated, or just 2 are correlated, like that, so we will call it as a multicollinearity problem exists in our model. Any example for the multicollinearity? The simplest example can be, say you are regressing the say average monthly spending on food in a city of, say, any New York. Okay, so you have to calculate like what is the general spending amount of any individual on food on an average, like that. Okay, so for this you have like, you will have your intercept. So we are concerned with this x1, x2 and x3. Okay, so say first x1 is your income, monthly income. Second is price of car you own. and third is say price of house you own and you are citizen of New York, right? So this is your regression model. If you just see it intuitively, you can identify the problem. So there is a problem with this particular part. What is the problem? Collinearity exists just in the example, just in the illustration. And this is one of the ways to identify multicollinearity. So you have to think about the practical case study, like if there is a chance that these three variables are correlated. So here see, if you have higher income, obviously you are more likely to have highly priced car, okay, costly car, BMWs or Audis like that. And again, this is related to the price of your car. So here your income part is directly correlated with the price and the price of your car and price of your house. Say if you have expensive house, you are more likely to have expensive car. And then obviously because these two are expensive, automatically you should have the higher income. So this income is correlated with the price of your house and price of your car. So we can say that yes, there is a collinearity, multicollinearity in this model. If you do this type of regression, then we will call it as a multicollinearity exists. Okay, so let's read out the theoretical discussion, the theory part of this. Okay, what is the multicollinearity and what are the statements you are supposed to remember? So multicollinearity is present when the independent variables are highly correlated. It violates the fundamental assumption of regression, which is the regression. All the independent variables are independent and identically distributed. Or I will rephrase the statement again. All the explanatory variables are independent and identically distributed. This is our fundamental assumption, right? So these are not the independent, these are correlated. Okay, this violates the assumption. Perfect multicollinearity is when the independent variables are perfectly correlated. It's like a very high correlation, okay, in all these variables. This can be detected by regressing one independent variable with the combination of the others. So first step, how to identify the multicollinearity. Just see here. So this is your model, B0 plus B1 x1 B2 x2 B3 x3, like that, right? And as we discussed, this is your income, this is your price of car, and this is your price of house, right? So first thing is to identify multicollinearity, you have to regress, say x1 or say x3 with B1 x1 and B2 x2. Okay, so this will be your regression model to check the multicollinearity. So now here we are trying to see if there is a high correlation of x1 and x2, that is your income and price of your car with the price of your house. So if you have say high price and high income and high price of your car, then automatically what will be the impact on the price of your house? If you find yes, this provides a really good coefficient of determination, meaning this particular part is able to explain x3, right? Meaning this is correlated. So this is the first way to identify the multicollinearity. Now see, while the multicollinearity does not affect the fundamental regression assumption statement, this can be confusing. So we are concerned with the high collinearity. Okay, so if there is a multicollinearity, it should be high, then there is a problem. Because see, if you take any regression model, there will be some correlation between the independent variables, small, a bit of a correlation, right? So in general, multicollinearity is not the problem, but the problem that is it does not violate the fundamental assumption, that is simple multicollinearity. Perfect multicollinearity is a problem. Simple normal multicollinearity is not that a big problem in the fundamental regression assumption, but it compromises the reliability of the parameter estimates. As soon as your reliability of the parameter estimates is affected, your model is not stable. Okay, so there is a problem with the model, right? So you have to remember this. So multicollinearity causes a problem for your model, that is, it compromises the reliability of the parameter estimates. Now, effects and detecting the multicollinearity. So first is the effect, then we will see the detecting multicollinearity. So what is the effect? Effect is, it increases the probability of the type 2 error. What is the type 2 error? Try to recall. I will not explain intentionally. Okay, if you are not able to recall, just pause it, visit your hypothesis testing chapter, see what is the type 1 error and type 2 error. If you do this, you will be able to remember type 1 error and type 2 error for long. If you are not able to recall it, if you are able to recall it, good, right? Now, type 2 error is the probability of incorrectly concluding that variables are not statistically significant. Okay, this is a problem with the effect of multicollinearity. There are also other effects of multicollinearity. Like, see what will happen if there is a multicollinearity, then I guess we have this discussion. No, we don't have that part here. Okay, I'll just give you the, like, what is the problem. Okay, further problem, I guess it should be there. Okay, not directly discussed in here. I'll just show you. Now see, if there is a multicollinearity present in the model, then this and this, because these three are correlated, the first effect will be on your coefficients. Okay, so coefficients, if you see these particular values in general, okay, so these coefficients will not be able to explain individually the model much. Okay, so if you just take one coefficient, then it will not be able to explain, but if you combine all the coefficients, then it will be able to explain your model. Okay, so there will be high R square. Okay, so this is one part. Second part is, because this type of problem is there, chances are that it will cause some problem with the these values and the prediction value. Okay, so this is general part. I guess we should discuss it more formally to explain like what is the problem. I think like we have the discussion. Just let me see, because it was there in the previous curriculum. Right now I don't, like, I checked in the book, there is not a discussion relating to the how the multicollinearity affects and all. Okay, this is just a very basic, this is the only effect discussed. There are other effects as well. There are two or more, three other effects which are related to your equation and the estimates. Okay, now detecting the multicollinearity. We will drop the discussion for this particular part because not covered in the syllabus, and it will create just unnecessary confusion. Okay, now see, detecting multicollinearity. If the model variable has very large p-value and high R square, that is, individually your variables are not able to explain. High p-value means it will get rejected, right? Sorry, null, it is statistically not significant, right? So high p-value indicates not statistically significant, but if you see the model, there is a high R square, meaning model is very well explained, like variables are very able to explain it properly to your model because of the high R square, say 90%, 95% and so on. But your individual variables coefficients are not statistically significant. So your variable is not, independent variable is not statistically significant. So x1, x2, x3 in individuality they don't have any value, but when you combine it, it is able to explain it, meaning there is a multicollinearity. This is a one way to identify it. So that is, the variables are statistically insignificant, but model has the high explanatory power. There is one more way to detect the multicollinearity, which is a variance inflation factor, VIF. Okay, so how to do the calculation? So calculation of the VIF for the explanatory variable. So there are steps, you are supposed to remember these steps. So step 1 is calculate R square by regressing your independent variable in question. Here we are taking say xj, or in our previous like in our example we took x3. So x3 is our variable in question, and we will regress it with the other variables x1, x2 and so on. Okay, so this is the first part, and using that part you have to get the R square. Automatically you will get the R square from the model, right? Step 2 is you have to calculate the VIF, variance inflation factor. This VIF is calculated as 1 divided by 1 minus R square. In case you get the question in exam about detecting the multicollinearity, first part will be provided to you, that is R square of this model will be provided. Okay, you will get the R square. The next step is simply calculate your VIF. VIF calculation is very simple, 1 divided by 1 minus R square, simple, right? And when you get this, you have to simply see if the VIF is greater than 10, or which alternatively means that is because we are taking the formula 1 divided by 1 minus R square. This also means that R square is greater than 90%. So variables are problematic. So meaning we can say that yes, the multicollinearity exists in this model. Okay. Next is the correcting the multicollinearity. Now what is correcting multicollinearity? Now you know the problem, you have to solve the problem, right? Solve the problem. So first way is to omit one or more correlated independent variables, but not always easy to identify source of multicollinearity. It is very easy to discuss, like this is the multicollinearity, and I am giving you example which is very intuitive. Okay, so where I am taking income, price of car, price of house and so on. So if this is the problem, then what can we say, like if this type of scenario is there, then it is okay to find out the multicollinearity. Now imagine like you are trying to identify the economic condition, and you are taking the different parameters of the economy, and now this particular economic parameters are so entangled with each other, so intuitively you cannot identify like which one is highly correlated with other, so that might create a problem. So the next step, which is, that's why we are saying that this is not very easy to do it. So statistical procedure is to do this stepwise regression. So stepwise regression is, you will start with say 2 variables, then you will keep adding the variables, and you will see like if this results in this particular multicollinearity problem, then you will drop that variable like that. So stepwise regression is the one of the solution. There will be one more impact. The impact is like your regression, your coefficient will drop like that. Okay, so again, I'm not able to discuss this particular part. I want to, but not able to because not covered in the syllabus. Okay. Now, including and excluding relevant variables. So, yeah. So now there is always a question. So question is, if you should include the variable or you should exclude the variable. Always remember this, including more variable will obviously increase your explanatory power, might increase your explanatory power, but it might create a problems like multicollinearity and so on, right? If you exclude the any variable from your model, there might be a problem that you are dropping a particular variable which is important for your regression model, which is affecting the regression model. But there is always trade-off. This is known as the bias variance trade-off. Okay, so you should go with the bias or you should go with the variance, and you have to always check with the trade-off, like what you want in your regression model. Now here, first is this. So excluding extraneous variable does not pose any risk for the model if the result, sorry, I'll just read it out. Okay, now including the extraneous variable does not pose any risk for the model, as it is it will result in decline in adjusted R square and will be dropped anyway. Question is, what is extraneous variable? Extraneous variable, or the variable, we can also say it as variable, which is not important for your model. Okay, so say very simple, extraneous as in irrelevant variable. In simple terms, we can say irrelevant variable. You can, in your regression model, you can add any value, any variable in your model. But if you add this particular type of variable, extraneous variable, so this variable does not pose any risk for your model, because there is a simple explanation for this. Your adjust, because we know, like if you add extra variable which is irrelevant, what happens? It will decline your adjusted R square. Okay, it will result in declining an adjusted R square. If the adjusted R square is declined, we know what we are going to do. We are going to drop that variable. So because you are going to drop that variable, it is not a big problem for us. Okay, it will be dropped anyway. Next is, omitting the relevant variable can produce a misleading result, meaning your model will not be robust and so on. So omitting variable bias, omitted variable bias. So this is the bias. Okay, so we saw bias variance trade-off. So bias is this, that you are omitting the important variable, the relevant variable. Is present when two conditions are met. You have to make sure that two conditions are met. So omitted variable is correlated with the other independent variable in the model. We are not talking about the perfect correlation. Okay, we are just talking about the normal correlation. Okay, it is relevant for the model. The omitted variable is determinant of the dependent variable, meaning, say this x is determinant of y. Okay, that is, say price of your car depends on your income. So if you are dropping income as a variable, independent variable in your regression model, the first problem is this only. And then it is correlated with the x2 and x3. Okay, so these two conditions must be there. Okay, now if this is the situation, like you have the omitted variable bias in your model, like you are omitting the variable, so there will be a problem. Okay, in this situation, correlated portion as in the correlated portion of this x, which is correlated with the x2 or x3, this particular portion of the excluded variable, this is our excluded variable x1, will be picked up by these included variables, which is x2 and x3. And the remainder, that is, see, x1 creates an effect on y. But if you drop the x, then what will happen? There will be two portions. Correlated portion will get merged with the x2 and x3 in your model. Okay, and the remaining portion will be captured in your error. Okay, so it will bloat your error, it will increase your error. Size of the bias depends on the correlation, like how much is the bias. Bias is the omitted variable bias. So if the high correlation is there, then the bias will be higher, and so on. And hence the coefficients would be biased and inconsistent. Okay, so this is about the including and excluding the variable. Okay, then there is a bias variance trade-off. Remember the key points here. Model with too many variables or too many x might explain the variation well in sample, but poor performly out of sample. Generally, this is what we do here. So we take the sample, we do the regression on this sample, and then we see out of sample, meaning the observations which were not the part of your sample. Okay, so this is the basic thing. So observations which are not the part of your sample, meaning, so say you have 1000 observations. Out of 1000, you are taking 300 for your sample and remaining for your testing purpose. Okay, out of sample. So remaining 700 observations will be considered as a out of sample. Okay, so model with too many x might explain the variation well in sample, but perform poorly out of sample. Okay, Then there is a overfit. This will result in overfit. Larger models have high bias errors and due to the inclusion of many variables and hence lower R square, adjusted R square it should be. Okay, so overfit larger model as in the models which are able to, like, based on the sample, it is able to like properly explain everything. Okay, and these models will have higher bias errors due to this inclusion of many variables and hence the lower R value. This is a statement you are supposed to remember. Again, not possible to explain in a theoretical discussion. You have to remember. Okay. Then dealing with the bias variance trade-off. So first is general to specific model. So start with the largest model. Like you have say 20 variables in your mind. You will combine all those like variables and then you will start with the large model. Okay, and drop the variable with smallest t-stat one by one. So you produce a model with 20 variable, see which one has the lowest t-stat, that is lowest t-stat meaning that variable is not statistically significant, drop it. Then rerun the model, then see which one has the lowest t-stat, drop it, and keep doing that till you get all the t-stat which are statistically significant, like that. This is a general to specific model. Then we have m-fold cross validation. So those who are taking the R classes, you will see both these things happening in your programming. Okay, so we will see, we will see practically how all these things are done. That's why I'm saying it is difficult to explain in theory. Then this is a m-fold cross validation. So this involves dividing the sample into m parts and using one part as a training and other as a testing validation for the out of sample validation. As we discussed here, you take say 1000 observations, 100 goes for your in-sample testing, which is a training data set based on which you are modeling your regression equation, and remaining say 900 are your testing data set. So once your regression model is done, you will try to check it with the testing observations. So you will calculate y hat for this and you will check it with the actual variable, actual y, and this will produce some variances or residuals, and then we will see if your model is working fine or not. A set of candidate models. Okay, so this is a m-fold cross validation model. So m-fold is generally used for say 10 or like you have say 20, yeah, as we discussed, like you have certain observations. So one part m is used for m part is used for training data set and 1 minus m is used for the testing data set. So here we are taking 100 for training and remaining 1 minus m, which is remaining, are for the testing data set. Okay, so a set of candidate models are first determined and then tested using the procedure, and models with the lowest out of sample error is selected. So procedure is very simple here. You have in sample, out of sample, 2 observations. You will have like say 10 set of models with the different combination of independent variables, right? Then you will keep doing this in sample and out of sample testing, right? In sample for training, out of sample for testing, and you will get a residuals. So whichever model will have the lowest sample error will be selected as your regression model. Okay, residuals and relative strengths. Here we are talking in relation to this particular residual. So the magnitude of the residuals is standardized and residual over plus minus 4 SD is considered problematic. So in these models, in this particular part, if you have any model which is producing residuals which is more than plus minus 4 SD standard deviations, then we will consider it as a problematic. Where you will get these values are like software based. Software will provide you all the values. Okay, so we saw in the previous lecture like how to do the regression. Now this is the part. Okay, so you know the regression values and you have to apply this particular knowledge to those values. And whatever we are going to discuss here, like whatever we are discussing here, which is a stepwise regression and so on, like everything can be done with the help of your software, and software will provide you values, and again you have to drop a variable or like that, you have to decide. Identifying outliers. Assumption of the regression is no outlier in sample which might skew the result. Okay, this is one of the assumption. Cook's measure is used as a metric to identify the outlier. So there is a measure, specific measure designed to check the outlier, which is a Cook's measure. So you have to remember this, the Cook's measure is used to identify the outlier. Large values of the Cook's measure indicates that the dropped observations was indeed an outlier. So there is a particular process for the Cook's measure. Again, with the software you can directly calculate the Cook's measure, not a big problem. Here in this particular calculation, you have to simply remember these values, like outlier is the problem in the regression equation. Okay, outlier observations are the problem. If you have the outlier, you will go with the Cook's measure. Higher Cook measures means that the dropped observation was indeed an outlier. So these are the three things you are supposed to remember. Again, the same explanation why we are not discussing it in detail, because it needs a practical application to see it in detail. Practical application is not testable for your exam, and it will just complicate or increase your discussion because you have to be focused for your exam, right? Again, for the R students, we will see everything in everything happening in program. Okay, so that's all about your regression diagnostics. Once you are done with this, do a proper revision, read it again and finish regression properly. After this, we will start the time series, which is the regression but with the time series. That is, the observations are time dependent, okay, in time series model. So we have 3 chapters on the time series model. Again, the discussion is pretty similar to the 2019 session, but here we have some change in the recording. Here this time I will use more examples, real life examples in theory, okay, in discussion, and then we will see the time series. Okay, so even if you are the old student and watching this lecture, make sure you watch the new lecture for the time series. Okay, so that's all about the regression diagnostics. See you in the next chapter. Thank you.